So let's move on then and talk about numerical models. All right, we just went through derived an analytical solution. Now we want to kind of flex the numerical part of our toolkit. So today is going to be I'm going to go through, I think, 4 or 5 different numerical methods. So I'm going to go pretty quickly. I'm kind of assuming you at this point have seen numerical methods to some degree before, but there's some new stuff I think that you probably haven't seen today. So we'll go through stuff first that you probably have, and then move on to the more complex. And I'll show you what the MATLAB and Ease code will look like for these. And again, there's a ton of examples in the folder on for lecture. So if you want to try out these different methods, you want to use one of them for your homework next week, you can go to those examples as a starting point. Okay, so for a numerical method, let's take our same problem. Again, we decided we could solve this analytically, so we don't have to do the numerical method. We could definitely do it analytically, but just for the sake of kind of comparing apples to apples, let's do it this way. So the primary thing we need to do for a numerical model in a transient setting or non-steady state setting is we need to come up with what's called a state equation. Okay, so a state equation is just an equation that gives you the relationship between the current state or the current state of the system. So like, let's say I know the temperature right now in my system, and I know the conditions, whatever ambient conditions or properties of the body. From that information, you can calculate the rate of change of temperature with time using a state equation. So a state equation, again, is just a relationship between the rate of change of temperature with respect to time, given the current state of the system. Right, and I always point out that this is not the same thing as an equation of state from thermodynamics, right? That has to do with like enthalpy and the properties of a fluid or whatever. This is a state equation. Okay, so our goal for this is to use the energy balance on a control volume, a finite control volume, and use that energy balance to come up with an equation for d temperature, d time, given the current state. Okay, so let's look at how we do this. The first step is going to be we take our domain. So here we have some temperature on this axis, and then we're going to plot that temperature as a function of time. Right, so we take our domain, and the first step is we break it up into a bunch of little finite time steps. Right, here we have a finite time step delta t that's greater than delta t as it goes to 0 or whatever. It's some finite step. Maybe it's 1 second or 1/10 of a second. But we discretize the domain. So we do that by saying, just get my notes here. So we do that by saying, let's define some delta t, some time step to be my total simulation time, which we'll call t sim. It's the time I want to evaluate this problem over. And then let's break that up into m-1 segments. Okay, where m is right here, m is the number of time steps that I want to have. Okay, again, we're doing m-1 because our first time step t1 is at time 0. You always want to have a node at time 0 so you can enforce the initial condition easily. Okay, so with that, then we would provide a list of nodes. So we're going to call these nodes J now, just to keep it separate from the spatial nodes. Tj, and so every Tj is going to occur at j-1 over m-1 times the total simulation time, t sim. So that's going to be true for all j in the span 1 to m. Okay, same thing we did for our spatial domain, just now we're doing it in time. Okay, so then let's talk about so we have our domain discretized. Let's talk about some techniques that we can use to model this numerically. So the first one we're going to go through, and one you've probably seen before, at least from 364, is the Euler Technique. Okay, so Euler Technique, the approach is as follows. We've got our ODE up here, right? We don't go through and solve the ODE. That's the whole point of the numerical models. We just get to the ODE, and then we develop a set of algebraic equations that go with it. So the Euler Technique says I can take some temperature T at J plus 1. I can predict the temperature at the next time step, J plus 1, based on the temperature right now, Tj. So that's equals Tj, that's the current temperature, plus the derivative of temperature with respect to time, evaluated at T equals Tj and time equals time j, right, times the time step. And that should be pretty clear from the definition of a derivative, right? So pretty straightforward relationship. We're saying take the temperature now, look at my slope of the temperature with respect to time, step forward in time on that slope. That's my next temperature, right? It's a really straightforward technique. Okay, so this is true for, by the way, for j equals 1 to m minus 1, right? Because once you get to m or m minus 1, you are now predicting the mth, is that a word, mth temperature. So that's as far as you need to go on that one. Okay, so that's the Euler technique. How do we actually get to this derivative here? So let's see. If you just look over here, right, we have our derivative with respect to time, and we have some function here that is just a function of the temperature. Right, so when we're saying I'm going to take dt over here, all you're doing is you're taking this right-hand side of this equation and plugging in the appropriate temperature where it appears in that equation. Right, so you're always going to have to start off for your problem by deriving that ODE, getting to the point of having that ODE for whatever problem it is that you have. You always have to do that part of it yourself. Once you get that far, then you can just take that equation, it may look different from that, and plug it in a numerical setting like this. So let's see how that actually would look. So let's take an example first of going from T1 to T2. So if I want to predict T2, I'm going to start with T1, and I'm going to take that derivative with respect to time, evaluated at T equals T1 and time equals time 1 times the time step delta T. Okay, so plugging in our actual equation here, we say T2 is equal to T1 plus, well, what is dt dt? It is, it is T infinity evaluated at time T1. Okay, and then minus T1 divided by tau LC times delta T. Right, so this is, you can see how it kind of works here. We have an equation of state, our derivative right there on the right-hand side, the second term. We're evaluating that equation, we're evaluating that state equation at that first temperature and at that first time, and that's the derivative that then gets us a step to the next one. Okay. So again, Euler's pretty simple, and it's what we would call explicit. So let me, just to finish this thought. So we've done this for T2 and T1. The next step is you just, any place you see 2, or you just do this for the first one, any place you see 2, we'll make that J plus 1. And any place you see 1, we'll make that J, right? And now you have your set of equations that you need. Okay. Of course, that's going to live within a duplicate in ease, or a for loop in MATLAB. Okay. Any questions on that so far? Yeah. Yeah, that's a good question. I think so. There's a couple of factors that I usually think about. One is if whatever you're evaluating really needs like heat transfer libraries, like correlations or properties for steam or something like that. That's typically when I would always go to ease for that, because it's so easy to use it for those things. If it's a numerical model like this and speed is important, I think MATLAB or a programming language will be much better. Ease is really, it's a really nice tool, is like a, I don't know what you call it, like a sandbox, like you kind of play around with it and kind of get the feel for things. But when it comes to actually heavy duty modeling of problems like this, I think you want to probably use MATLAB. Okay. Okay. So let's talk a little bit about, I think I skipped a slide in you might have an extra slide that I'm going to have to fit in over here. So let's talk a little bit about the properties of Euler's technique and how we can understand some of the error that's involved here. So I'm gonna zoom in because I think you have an extra blank page and I don't. Okay, so the first thing we want to note is that Euler's technique is something called first order. It's first order. Okay, so first order has to do with the number of times we evaluate the derivative, right? Or if you think back to like a Taylor series expansion, we have the first order term, the first d dt term, and then we have a second order term, which is d squared, dx squared, or whatever. Right, so the order of the technique has to do with how we kind of truncate off the error in those solutions. So Euler, you can see as first order, right? We're just taking one evaluation of the derivative, and that has implications on the accuracy of this method. Okay, so what do I mean there? So let's look at the example here. So let's say we want to predict the temperature for some time plus some time step delta t. Okay, so if we kind of expand out what the actual exact model of this would be, we would say, okay, well, it's Tj. What is this J? Let me just rewrite this. So let's say this is, sorry, Tj plus 1. We'll just be consistent. Is equal to Tj plus my first order estimate, dt dt. So this would be at t equals tj and time equals time j. Right, that's going to be true for all the terms. So I'll kind of stop writing it. Times delta t plus what's my second order term? Well, it's d squared t dt squared. We're evaluated the same thing times delta t, but it's delta t squared, right? Delta t squared, and then we have in the denominator 2 factorial. Okay, so that's the second term here. We could keep going. So then the third term would be what? D cubed t dt cubed. Evaluated at the same thing, and then this is going to be the time step delta t cubed over 3 factorial, so on. Okay, so Euler's technique is saying, I'm just going to take the first term, right? The tj plus dt dt for the first order term. That's going to be my estimate of the slope. It's ignoring everything else, right? So then all of this stuff over here is actually error, right? There's an error between your numerical solution and the true solution of the order of magnitude of whatever the largest term is here. Well, the largest term is what, d squared t dt squared, because as the time step gets smaller, right, that delta t squared is going to be much bigger than delta t cubed. So the second term is actually governing the error, right, the local error for this problem. Okay, so if we write this out, the local error for this is going to be equal to some evaluation of that derivative, which we'll just call k, conceptually called k, times delta t squared. Right? That's the local error that's associated with throwing away those other terms. Now the global error for this, if we every time we evaluate this equation and jump from node to node, if we're getting error in proportion to k delta t squared, the global error is actually going to start accumulating over time, because you could make a mistake or have a slight error for one jump, and now you're continuing on that trajectory. Right? So the global error is kind of cumulative. So the global error is, say, approximately the sum of the local error, which is approximately equal to m. Okay, m is the number of time steps. So how many opportunities we have for error, times k, which is the evaluation of the derivatives, times delta t squared. Okay, so that's also approximately saying delta t sim divided by the time step delta t times k times delta t squared. Okay, so this is saying, okay, one of the delta t's canceled out. So we're saying that the global error is actually proportional to delta t to the first power. Okay, so where am I going with this? Like, why is this important? Well, it's saying if I have, let's say I pick m nodes to be 11, right? And I get a certain error associated with that. How many additional nodes am I going to need in order to drop my error by an order of magnitude? Well, it's scaling according to the delta t to the first power. And so I'm going to need an order of magnitude more nodes in order to get an order of magnitude reduction in error, in global error. Okay. So if we, let's see, some stats on this. Oh yeah, here they are. So let's say I choose m equals 11 for this problem that I'm doing. So if m equals 11 and my delta t is at 0.04 seconds, that leads to, if you calculate it out for this exact problem, it's 8.5 degrees Kelvin, right? That's our local error for predicting the temperature for this numerical solution. Okay, so if I want to reduce the error, let's say I go to m is equal to 101 nodes. And so for 101 nodes, that gives us a delta t of 0.004 seconds. And my error goes to 0.7 degrees Kelvin. Okay. So it's not perfect scaling, but yeah, like pretty much an order of magnitude reduction in the error for this problem. Yeah. In that, yeah, so it's the nomenclature in the book, but it's just that K up there in the middle is the evaluation of the derivatives, but it is proportional to the temperature itself. So down here, this is degrees Kelvin. Yeah, sorry, that's confusing. Okay, so that's Euler's method. The other thing to point out about Euler's method is that Euler's method is explicit. So Euler's is explicit. Right, that means the evaluation of Tj plus 1 only depends on the current state of equations, right? On the current temperature Tj. So you don't have appearing on the right-hand side, you know, Tj plus 1. It's only on the left-hand side of that equation. Okay, and we'll see examples where that's not the case.